So I'm Brent Compton. I look after the reference architecture team for storage at Red Hat. So here's a question for you. So finish this sentence for me. The good news is that Ceph and Gluster work with any commodity hardware. Open. So that ends with a comma. The good news is that Ceph and Gluster work with any commodity hardware, comma. And Matt, you started to say except. Okay, that's one direction you could take it. There's no right answer. Just curious what's on your mind. How do you finish that sentence? Please, Dor. Takes a lot of babysitting. Works with any commodity hardware, comma. Anybody else? Any takers?
But now we realize that commodity hardware is not really cheap if you want to do it right.
But now we realize commodity hardware is not really cheaper if you want to do it right. Okay. Again, no right answer. Just interested what's on your mind. Other takers. Works with any commodity hardware, please.
If you know how to size your solutions based on your workloads.
If you know how to size your solutions, the solution is based on your workloads. And that's kind of, I fibbed a little bit. That was kind of the answer that I was looking for. Frequently the question we get is, hey, this is fantastic. It works with anything. Long pause. So, what do you recommend? We get that question all day, every day. And I'm sure you all, in providing storage services to your company's teams, get that question all day, everywhere. And so that's what my team focuses on, is helping to answer that question. So what do you recommend? Great detail from the Chris's at Bloomberg. Good detail from the Chris's at Cigna. Any other Chris's in the room? Just curiosity. Good. So we've published performance and sizing guides with Supermicro and Ceph. These are, you can Google these out there. We've published performance white papers with Cisco, with Ceph, performance white papers with Gluster and Cisco. Have some interesting work going on right now. A lot of people say, so if you attended OpenStack Tokyo, there was a lot of talk in the Ceph space about, I'm running all these workloads. In fact, it was where the Chris's, the second set of Chris's ended off of not every workload is appropriate for Ceph. One of the things that we hear is as we use Ceph or Gluster as our cloud storage platform, we want to add workload after workload after workload, just one at a time. Is this workload, back to your point, does this workload fit the profile of Ceph or Gluster? I'm going to continue to say Ceph, but it could be Ceph or Gluster. Does it fit the profile? So a lot of interest in databases, MySQL and PostgreSQL probably on the forefront of those. So one of the fun things my team is currently working on is we're about 4 months into a study with the MySQL community of MySQL on Ceph. We're doing all spinner-based cluster, just cut over this week to an all-flash cluster. So that's we have standing labs with Supermicro and a standing lab with Quanta QCT. We also have the following underway, and I share these names with you in case you have areas of interest. We're always interested in peer reviews. Community-based. That's the lifeblood of our work, is working with you as you benchmark, we benchmark. Together we learn optimal configuration. So I'll share these names with you again. So MySQL High IOPS reference architecture in the Supermicro lab. With the MySQL community. It's backed by friends at Seagate are in there, Mellanox is in there, and whatnot. We're just publishing next week the Quanta QCT Ceph reference architecture. We're doing an interesting one that's near the tail end with Intel on degraded state operations versus steady state. Something that we all love to share benchmarks when things are running perfectly, but what happens. Actually, I loved in the first pair of Chris's when they talked about we've learned to tolerate some pain. Well, that's kind of the essence of what a lot of these architectures are intended for, right? Is you deal with it. That's what it's designed for. Is failures are expected. So anyway, degraded state reference architecture with Intel on Ceph is a fun one. Very interesting. Also doing a Quanta QCT Gluster reference architecture. Doing one with SanDisk InfiniFlash, so the all-flash stuff there. working with Samsung on some flash architectures, and got a new lab spinning up with Dell. So anyway, those are the few of the reference architectures that our team are working on. Okay, so this here is, they've been asked me to speak about 6 basic design principles for architecting Ceph clusters. For some of you, given the nature of your presentations some of the questions that you raised earlier, for some of you this will be relatively basic, but I'm assuming that there's an element of the audience here that this is maybe in the middle of the road for. So these are basic design principles for architecting clusters. Okay, so all starts here, basic building blocks, right? No real surprises. Okay, so here are those 6 key design principles. Again, straightforward, basic. This is nice to have this sanity check as you go into this thing. First is where the second pair of Chris's end up is not every workload is a fit. Okay, so qualify the need for scale-out storage. So answering, I think it was, James, your question you asked. So like, for example, which ones? Like small ones. People who say, I need 100 terabytes for this, low latency, high ops. Use something else. Anyway, that's one of the examples that we see. So anyway, so the first is qualify the need for scale-out storage. Second is design per Ken's comments, is design for the target workload I/O pattern. Third is choose the storage access method, because that controls what set of choices you have in a number of cases for farther on architectural choices. Identify the capacity so that you can then understand what density of server. A lot of talk about, I want to use ultra-dense servers. I mean, load it up. I want 72 drives in my server. Well, there are performance, there are cost, capacity, and performance considerations for that. So determining, as well as fault domain considerations. So determining your capacity is directly related to determining your fault domain risk tolerance. And then finally, is selecting the data protection method. So these are kind of just 6 basic design principles of architecting a Ceph or Gluster cluster, so that you can spit out get a sense for where to start with the hardware design. Next slide, please. So we approach hardware designs kind of just in this way. And as you've seen, it's relatively straightforward. So we deal with a 3x3 matrix. So this is the lens through which we do our reference architectures. IOPS optimized workloads, throughput optimized workloads, and cost capacity optimized or cost capacity archive optimized workloads. Likewise, from a capacity standpoint, we say, okay, there's an extra small OpenStack starter, small, medium, large. And so now, clearly, every single environment has a mixture of these types of things, but this gives a starting point. So as we do reference architecture, we can say, okay, right now, for instance, with that MySQL study I mentioned, we're working with a lot of IOPS optimized anywhere between here and here type configurations. We just completed a high density study in the Supermicro lab, which was more in the cost capacity optimized petabyte, 2 petabyte plus. And as you heard from the first pair of Chris's, as they split out the object storage, for instance, you can dramatically change your cost profile of your infrastructure by designing the infrastructure according to the workload. And particularly with Ceph, makes a big difference, your cost profile. So this is the lens, this 3x3 matrix is the lens through which we view reference architecture. Next slide, please. So here are just kind of starting with the sequence of these slides. We start with the answer and then go backwards through the design principles. And this is just, as the title says, broad server size trends. So operative word is trends, meaning you may be doing something different, but that's okay. So broad trends. So server size, you can see superimposed on this 3x3 matrix. IOPS optimized, seeing a lot of folks putting 2 to 4 NVMe form factor PCIe drives inside of a server, or a dozen 2.5-inch SSD SAS SSDs. And note the asterisk for IOPS optimized emerging. There's just the body of work for characterizing Ceph's performance on IOPS optimized workloads is smaller than the body of work characterizing Ceph's performance for throughput optimized and cost capacity optimized. Now it's growing, but it still merits an asterisk. So one of the things, for instance, in this category here, we just did a lot of work, again, with the MySQL community with with spinners behind RAID controllers with large write-back caches. So single volume, single disk RAID 0 volumes for Ceph OSDs with large write-back cache. Pretty interesting results. Write-back cache is doing what it's supposed to do, making random reads really efficient to back-end spinners. So some interesting results there. Not quite ready to elevate to a broad server trend, but again, just a reflection of evolution of the body of results out there. Next one. So throughput optimized, cost capacity optimized, and you saw it here today. 12 to 16 3.5-inch bay spinners. Very common for this space here. As you get into the larger cluster sizes, we're seeing nice performance on 24 to 36 3.5-inch bay servers. Nice performance. The I/O backplane being sized well for the number of drives. So we're seeing nice scalable performance from what you get from a 12-bay server to a 36-bay server. Nice. This over here, so 60 bay, 72 bay. That was maybe about 9 months ago. There was a lot of questions in the industry about well, hey, these 4U servers out there, how will they perform with Ceph? We see them as a great choice for cost capacity optimized type workloads. The I/O backplane is still widening to effectively to not become the bottleneck to drive all the drives. But nice choice for here. Need one more PCI slot. So some broad trends. Next slide, please. So now we get into a little bit more granular detail in terms of, okay, so next level down. So IOPS optimized, clearly Rados block device, that's most of the IOPS optimized workload is going to be there. OSDs on all flash media. Note that my point earlier about seeing some interesting results with write-back cache in front of effectively absorbing the 4K, 16K random writes and providing a really nice shock absorber. Again, not ready to publish yet, but it's been interesting. It's interesting. Those, particularly when you're driving PCIe NVMe drives, they're going to soak up a lot of CPU. Good. That means you're getting a lot of work done through those things. So pay attention to the bin of your CPU there. Seeing a lot of work done with 26.9x. Yeah. You're running out of numbers, right? 2x replication with backup. Seeing another trend here about, people say, wait a minute here. What I read about all the time is 3x replication with Ceph Rados block device. Seeing a lot of folks saying, hey, with the improved MTBF and MTTR of flash, seeing a lot of folks saying, hey, that as I balance that with the cost. Seeing a lot of folks saying, I'm willing to go 2x replication with a nice backup. Gets me even more interesting is stuff Sage talked about before, the async replication for site mirroring and stuff like that. So good. And then another thing, check out is against the standard rule of, hey, I only want to have one OSD per device. A growing body of work showing multiple OSDs per NVMe flash device is, if you don't, you got a lot of idle capacity there. So some trends there. Next one down, throughput optimized. So clearly there can be throughput optimized Rados block device and throughput optimized object storage through gateway. Depends on the workload. So either can be throughput optimized. So OSDs on HDD media is the trend, of course, we're seeing there, mostly because it's a larger capacity play with dedicated SSD write journals. This is an interesting one. So standard 4 to 5 spinners per dedicated SSD write journal, comma. But one of our studies, we did a price performance comparison of, instead of your standard 12 3.5-inch base server, so you have 10 spinners plus 2 SSD SSD write journals. That's kind of the most vanilla Ceph RBD configuration. But So what if you instead do 12 spinners and 1 PCIe for a dedicated write journal? You could say, oh, single point of failure type of stuff. And for some folks, that may be outside of your risk tolerance. But price performance on a lot of servers is actually better. Doing, in our nomenclature, we call it a 12 plus 1, 12 spinners plus 1, in this case, PCIe flash, versus 10 plus 2. And by the way, we also did the same study on a 30 plus 6 versus a 36 plus 2. So just 2 PCIe dedicated write journals absorbing the journaling the writes for 18 spinners each. Anyway, that's just a side note on this here. This here, get away with mid-bin dual socket, good, 2650 class, 2670 class. Note here also, we've seen solid performance for if you're building lots of small, particularly these days, you have these 1U, some nice servers coming out these days. 1U fully hot swappable 12 bay, or 1 or 2U. But anyway, so less than or equal to 12 OSDs, get by with a single socket as well. I mean, if you're building out massive, petabyte upon petabyte type deployments, looking to save every last penny, you might want to look at that for, again, note, for less than or equal to 12 OSDs. And also note for throughput optimized, high bandwidth networking. Interesting questions on the second pair of Chris's about bonding. In our last study, actually the study is going to be produced with Quanta or released here in the next week or so. We used 40 gig, there he is, 40 gig Mellanox networking there. We tend to, in our benchmarking, we tend to go with 40 gig, just more straightforward than bonding. My team thinks bonding's a nuisance, if I can say that without, and we just prefer to go with straight 40 gig anyway. So in the linear scalability that we're seeing in terms of, and that's by the way, least common denominator that we translate things down to is how much work can you get done per drive? Whether it's a drive in a 12-base system, 24-base system, 36-base system, 48-base system, et cetera, how much work can you get done by drive? Because that's the least common denominator. So again, seeing nice linear scalability with Ceph on some of these up to, like, as we mentioned before, the 36-bay servers. But so that's somewhere between 12 and 16 drives. If you have large block sequential I/O, you're going to run out of network juice. So 10 gig is not going to cut it, somewhere between 12 and 16. Again, if you have a large block, if you're a throughput optimized workload and you have a large block, that's a nice point to be thinking of. For us, we cut over to a 40 gig networking. So that's that. Last point here, cost capacity optimized. One of the standard things as well, you always use dedicated flash devices for dedicated Ceph write journals, right? Well, no. If you're building cost capacity archive object storage, and again, that's the characterization of the workload I/O pattern, cost capacity optimized versus throughput optimized versus IOPS optimized. Ceph works perfectly well with co-locating the write journal on the spinner. So if that's the workload profile, why spend more than you need to in order to achieve the output? So that's another thing to note there. Okay. So it's just some broad trends. Back to the point about, okay, so the title of this little talk is 6 Key Design Principles to Architecting Ceph Solutions. This is just kind of back to the question of, the good news is that Ceph and Gluster work on any commodity hardware, what do you recommend? There's some broad trends that we're seeing right now, both in talking with people like you as well as from our own labs. Okay, now, back to the 6 design, then we'll finish up on the 6 design principles. And Ross, I'm going to give you back 10 minutes. Officially, you're supposed to be out on break at the top of the hour, but it's my promise to you that I'm going to stop speaking in exactly 10 minutes. Okay, Neil, mark, set, go, 10 minutes. So step 1, of 6 steps. Really basic step, just sanity check type stuff. Make sure that the workload needs scale out storage. So, and here's just a set of things you're probably most of you are familiar with. What are common clues? Well, do people talk about elasticity of the storage pool? Do people talk about consuming commodity hardware? Do you need to scale beyond a petabyte, a couple of petabytes? It's just tough to do on traditional storage. Another one I hear is, hey, I've got these dual controller islands out there. Sure, I can scale out one island at a time. This is another interesting one here. A performance capacity scaled independently. An interesting one to think about here. You think about like a FAS 8040. You can load that puppy up with as much capacity as you want, but it's still the same 2 hamsters running in the gerbil wheel, right? So that's the versus distributed storage. You scale performance and capacity. You need more performance. Use a different server profile. You need more capacity. You add more disks. So that's another element there. Ross already covered the last one. Okay, so that's step 1, qualifying the need for scale out storage. Step 2, please. Step 2, design for the target workloads. So again, basic things, sanity check type questions. Is it performance, from top of the list, is it performance versus cheap and deep? A lot of folks say, well, both camps, yeah? And then the next level of granularity, performance is more, there's more to performance than just a single word. Is it throughput optimized? Typically characterized by large block sequential I/O patterns, or is it IOPS optimized, typically characterized by low latency, small block I/O. Read versus write mix. Another thing that is on the previous slide. Standard people say standard tribal wisdom is, hey, erasure coded bad for performance, replicated good for performance. Performance studies show that if you have a write-intensive workload, erasure code is actually pretty nice. I mean, think about it. You're writing a whole lot less to the cluster when you're erasure coded than you are with replicated, particularly 3x replicated. So it's important, again, in architecting a cluster that's right and most cost effective. Step 3. Choose the storage access method, really fundamental type thing, but a couple of notes here. For example, double asterisks on block. So Rados block device is currently supported with replicated data protection only. So, things like that are important to know. Okay, if I'm going to use RBD today, RBD is not going to sit directly on top of an erasure coded pool. Notice how you chose the terms consciously. Cannot sit directly on top of a erasure coded pool. So, important. Next, step 4, identify capacity. So identify capacity, again, really basic thing. Why does this matter? Well, it typically matters in choosing your server chassis size. From a failure domain. We get, on a regular basis, we get people, a little bit less so, but like 6 months ago, people enamored with the 60 base, 72 base server, and they're cool for a purpose. And people saying, hey, I'm going to use that thing. Well, how big's your cluster? Well, I need a good half petabyte. It's like, well, yeah, that's like 1. Bad idea from a failure domain standpoint. And so, just really basic steps, sanity check level thinking here. To ensure that, so after you identify the capacity, next step, please, is then determining the fault domain risk tolerance. In other words, what percentage of cluster capacity are you willing to tie up in a single node? And it varies probably for every person in this room. It's a subjective question. But knowing that fewer cluster nodes equals more workload performance degraded during recovery. It's simple because each individual node needs to contribute more of its capacity towards recovery operations. Likewise, from a capacity standpoint, fewer cluster nodes equals more capacity per node reserved for absorbing the data that was on the failed node. So again, really basic principle type things, but important just kind of have in the back of your mind in architecting these clusters. So here's some guidelines. So from a Red Hat Ceph Storage minimum supported standpoint, minimum supported is 3 cluster size. It used to be a question we get all the time before. I'm grateful that, I don't know, Neil, if you see this as much now, but for a while it was like an in vogue question. What's the minimum cluster size? Like, this is scale out storage. Be thinking, you should be asking the other question, not the minimum. But anyway, so fortunately we see a little bit less now, but minimum supported is 3. That's not the same as minimum recommended. Minimum recommended is 10 for these reasons. So thinking kind of, okay, one node represents 10% of the cluster capacity. And then minimum recommended, we relaxed a little bit on the recommendations for cost capacity cluster because it's not performance-oriented type cluster, it's more of an archive-oriented cluster. So, okay, so step 5, determine the failure domain risk tolerance. And then the final step, step 6, is select the data protection method. Most of you probably know that this is probably the single largest factor determining the acquisition price of your cluster. I mean, if you need 1 petabyte of usable and you're 3x replicated, you're buying 3. Versus if you're, say, 8 plus 3 erasure coded, you're buying 1.38, something like that. That's going to make a difference on the pocketbook. So really important step in designing the cluster. So those are just 6 really basic, again, basic, in a lot of cases, common sense, just put them all in the same place, steps for architecting a Ceph cluster. Mostly applicable to Gluster as well, with a few exceptions. Okay, so with that, the closing slides are, so here are a few of the reference architectures that are out there. Performance and sizing guide. I was flattered earlier today. It's 44 pages long, right? 44 pages long. I was flattered that someone's actually read all 44 pages. It was a great thrill for us to hear that. And also the one on Cisco, the Scalable Informatics guys are here as well. They have a performance white paper out there. Last thing I wanted to say, we have something called the Ceph Performance Leaderboard. It's a fun place because, I mean, the thing as the second round of Chris has mentioned, it just nothing ever sleeps. The hardware innovation, software innovation, blah, blah, blah. And so people always want to know, what if I'm running a 24, 2.5-inch SSD, how's that going to perform, almost limitless permutations. Well, that's why we created the Ceph Performance Leaderboard, so you can go out there and say, I want to see what other people have, the results that they have. So right now it's this little poor man's Google spreadsheet, but it's going to go up on ceph.com with a nice dashboard, so you can have a nice way to just kind of find out what results other people are getting. The rules to entrance, the testing has to be conducted through Ceph benchmarking tool, just to get a base level of comparability between results. So Ceph benchmarking tool, which is published out there on GitHub. In case any of your folks want to play around with Ceph, want a really simple, easy, free sandbox to play around in Ceph, we publish, actually both Ceph and Gluster, we publish Ceph and Gluster test drives. These are hosted out on Amazon.com. Provided that you don't give these links to every university student in the country of China, we'll continue to fund this. But it's effectively, there are lab exercises. It's the full environment. You have a 9-node Ceph cluster. You have an 8-node Gluster cluster. Go out there, knock your socks off. At the end of 3 hours or so, you'll have done you'll have configured Ceph or Gluster clusters, done a bunch of permutations of those. Use them for your teams. Use them for whatever.
I liked your 3x4 matrix, but the question I have with the top line, was that before or after the redundancy? Because 2 petabytes plus triple replication is a big difference than 2 petabytes including the triple replication.
I have to think what we used in the reference architecture. I think we used usable in the reference architectures as a lens through which to view that.
Hi, just a bit of warning to people who just say CPUs are not important. Our friends at Scalable Informatics and us had a few tests at high capacity 100 gig parts of Ceph, which was great. We actually found that a lot of CPU cores were just busy, 100% busy chugging IOs. So it's something to consider when you decide what to put in. One socket, like you wrote, one socket for under 12 OSDs, but don't skim on the CPUs.
Especially if you're going to use NVMe.
Single stream versus multiple stream benchmarks. We discovered that the Rados bench runs multiple parallel streams, and you would get very good results in a lot of different configurations. That turns out to be dramatically different from single stream I/O. Have you looked at that, and is there any considerations order of magnitude different?
In our current benchmarking, we have not done single stream. I'm thinking about right now the one we have going on with MySQL. We have highly parallelized. In fact, so I realize I'm branching from your statement, but just the first thing that came into mind. So at our MySQL testing, for instance, we started off running effectively a single MySQL instance on each client. Where we ended up is containerizing MySQL and running, instead of one on each client, one big monolithic instance of MySQL, having many smaller instances, each running their own database, kind of reflective of the multi-tenant environment. So, in fact, I answered your question about single stream with another multi-stream type workload, but anyway, so that's the answer.
Just a quick point here. Laura sort of brought this up. One of the bits that we discovered during some of our testing in our lab at Scalable was basically you really have to worry about contention, but not just where you think you might have to worry about it. You have to worry about it at the disk layer, at the PCIe layer. You have to worry about it at the JBOD connection layer. You have to worry about it at the network layer. That is, most of the recommendations that we've seen over the past couple of years about how to design these things don't necessarily consider the contention aspect in a lot of these issues. We build things a little bit differently, so contention hits us in a different way than most other folks, but we still see it under extreme loads. And one of the things we found when we were testing the 100 gig scenarios is we actually started getting really interesting, very large thread count contention issues, which was part of the reason why the CPUs were spinning there idle for so long. It was amazing to see this and realizing that we had to go speak to a couple of folks at Intel and a couple of other folks to see if we could fix it. So I just wanted to inject that.
Joe's comment reminded me of something. It turns out that the memory allocator that's in the current Red Hat Ceph Storage is suboptimal. It defaults to tcmalloc 2.1. In the next release of Red Hat Ceph Storage 1.3.2, and actually 1.3.1 in use with, what is it, Neil, with RHEL 7.2? By default, it loads tcmalloc 2.4, and for small block random I/O, it's like a 3 to 4x. Not like 3 to 4%. That's like 300 to 400% difference. So it's all related there.
So very briefly, it's extremely sensitive to affinity in almost all aspects, because if you have a multi-CPU system and you start banging on a device which is sitting on a CPU which is non-local to that device, you're talking over your QPI interface, and guess what? You have two of them in your two-socket systems. And that means that is a consumable resource and you're going to fill it up. And we see this on a lot of our benchmarking. We have to work very hard to pin the processes to the appropriate socket, as well as pin the memories to the appropriate socket, and make sure that we actually load balance across network cards. One of the points that we didn't make in our performance report is that if you really want good performance, have two network cards, one on each PCIe bus, connected to each different socket. And hey, you actually get much better performance when you do that, curiously.
Thanks for the Q&A. Ross is going to take us to the next thing here. So last statement, which is, if you're interested in reference architecture, performance benchmarking, talk to me. We love working, peer reviews, that kind of stuff. Ross, over to you.